Hey there everybody, and welcome to the first video on the Epidemic Models unit. So in this video I just want to give sort of a global 30,000 foot overview of SIR models, which are the models that we'll be using to study the spread of disease. So the point of this video is just very brief, just to give a global overview with no math to set up these models. So let's start with just a little bit of history. These models were discovered in 1927 by Kermack and McKendrick. And as far as I am aware, their paper from 1927 was the first time that anybody tried to mathematically rigorously model disease spread in this kind of way. This image on the screen here is from their paper. You see this nice little infection curve here. These sort of curves are all over the news now for COVID-19, you know. So here's the first time somebody drew one of these curves, and it has this nice little, you can see the exponential growth up front, and then at some point along this path, this curve, there's an inflection point where the derivative starts turning, right? And eventually you peak here with a derivative of 0, and then down you go on the other side. So anyway, this picture here is a model of the plague, okay, an old-timey disease. This is from some island, I think off the coast of India. There was a plague outbreak there, and Kermack and McKendrick modeled it in the 1920s. Okay, what kind of diseases is this model meant to handle? Okay, SIR models can't handle all disease. There's no model that can handle all disease. SIR models are designed to model diseases that have two properties. The first property is that diseases are contagious via human-to-human contact. So something like malaria is contagious, but it's contagious via mosquito-to-human contact. Cancer, of course, is just not contagious as far as I'm aware. I'm not sure there's any cancer that's contagious. So anyway, so SIR models can't model the spread of malaria in a malaria outbreak in the tropics, can't model cancer spread. The diseases that we model also need to be recoverable in this sense. You have the disease for not very long, and then once you're done with it, you are immune for a long amount of time. So a disease like HIV, while it is contagious via human-to-human contact, right, you don't recover from HIV. So the kinds of diseases we are talking about are not malaria, not HIV, but instead diseases like the cold, the flu, etc. Let me just say real quick, the cold and the flu, I guess, you might think is not SIR modelable because they are clearly contagious, but they're not recoverable, right? People get the cold or the flu like every year sometimes, you know, so how could they be recoverable? And the answer is that when I say something like the cold or the flu, I'm referring to a specific strain of the cold or flu. So if you get the cold this year and then you recover from it, you are indeed immune for a while from that strain of the common cold. But the common cold mutates so quickly that by next year it's just a different strain. So from your body's perspective, it's like a different disease, you know. So anyway, so when I say things like the common cold, I'm just talking about a particular strain. So all that being said, the kinds of diseases that are contagious via human-to-human contact and are recoverable in this sense are diseases like the cold, the flu, chickenpox, whooping cough, measles, mumps, etc. Many of these diseases we've handled through vaccines, of course, right? Ebola, a bad one, no vaccine. SARS, so that was one of the other big coronavirus outbreaks previously. COVID-19, I put a question mark here because apparently, obviously COVID-19 is contagious this way. There's some debate, I guess, and I'm not a medical doctor, I'm not an epidemiologist, so on, all the caveats, right? But apparently there's some debate over whether you can, whether you're recovered, if you've recovered, if you're immune for a long amount of time. Apparently there's some debate about whether you can get reinfected at a later date. Right now the answer seems to be no. So it does seem to be recoverable in this sense. But anyway, I put a question mark there just because there is some slight debate over whether or not you actually are immune from it after you've had it. Okay, so the model works like this. So for diseases like the flu or COVID-19, the population can be divided into three groups: those that currently have the disease, those that have had the disease, and those who might yet get the disease, if you like. So we're hitting all verb tenses there, right? So people who are infected, people who have been infected, and people who might get infected are the three populations of interest. And of course, anybody in the population falls into one of those three categories. So the SIR model works by building differential equations for every one of those population groups. And these differential equations measure how the populations change over time. In order to get a given model up and running for a given disease, we only need to know three things. We need some estimate of the initial number of infected people. We need to know how long, on average, the disease lasts in a person. So if you get the flu, will your infection last 4 days, 8 days, whatever? We need that number. And some measure of how contagious the disease is. If you have those three numbers, you can get an SIR model up and running and start making predictions about how an outbreak will spread. I want to close this video by talking about this question. Are these models still useful? They were invented in the 1920s. Much math that was invented in the 1920s, especially applied math modeling, much of that math is now obsolete, of course, right? It's out of date. So are these models still useful, or are they just historical relics? Well, on the one hand, right, if they were just historical relics, I wouldn't bother teaching them to you. These models have been proven to be surprisingly robust. They are still quite a bit in use, not necessarily the classic ones that I'll show you, but models that are like them and are built on the same kind of reasoning. So SIR or SIR type models are very much still in use. If you Google Scholar SIR model, SIR and then model, you're going to get thousands upon thousands of hits, even dating back to last year. So the models are still in use. Lots of people think about them. They certainly aren't, like if you work at the CDC or the NIH or whatever, they're not like the only tool or even really the best tool that those people use. But they are still tools that those people think about. If you work at the CDC, I guarantee you there are computers there crunching out SIR predictions for COVID-19 right now. It's just part of a toolkit, a general toolkit. In particular, SIR models are good at sort of letting you think about like best case, worst case scenarios for how a given outbreak will go. And I really want to emphasize this. For those of you who subscribe to math modeling journals or applied differential equation journals, and I'm sure there's several of you, over the next couple of years, there's going to be a huge race to publish papers about COVID-19 that use SIR models or SIR type models to analyze the disease. So the kinds of questions you're going to look at in your homework, it's not like what you guys write will be publishable or something, but the kinds of questions we're going to be thinking about, certainly there are people trying to answer those questions right now with SIR models. So it's not just a historical relic, not just an academic exercise to think about these models and try to use them to make predictions. All right, so in the next video, we'll start actually building some of the math, start building some of these DEs to get these models up and running.